right, boys and girls, I'm Nick. We're going to do some maths. Slightly different format today. We've got a bigger, juicier question to tackle. I want to show a few things in 3D on some graphing software. So, no whiteboard, instead, spooky floating head. All right, so the question we're going to tackle today is all about 3D geometry, vectors, planes, angles, things like that. And it was submitted over on the Lungang subreddit. Go check it out for some cool maths questions. And actually, it was big enough that I figured let's use this as a good opportunity to review and think about some of these properties in 3D. So we're not just going to crank through the question. We're going to talk a bit about what it's doing, why we're doing it, and so on and so forth. And I'll try and show you a few pictures. In 3D, it's not always easy to drag us along the way. Right, so what is our question? So here we go. We got two planes in 3D. Now they're written in a weird way that you may or may not be familiar with. So we've got this expression in terms of a point and two vectors on the plane. All right, and we got two of them. Now already I want to use this opportunity to go have a little look-see at what that means. So let's see if this works. Let's pop over to Desmos. Lovely. So this first plane, pi 1, if we go back to it, making sure everything works, like I'm working off like 3 different screens. So if you're wondering where I'm looking, that's why. So this first plane has, let's get a pointer going so I can point these out. So we've got a point here and two vectors on the plane. So let's pop those in. So what it means is we've got this point here. So that is the point 1, 2, 3, and it's just floating about there. And then we've got the two planes, the two vectors coming off it. That is the vector minus 1, 2, 3, and then we're going to want the vector here. All right, so this is what the question is giving us for that plane, a point and two vectors to play around with. And what this means is if I start at this point and then travel along either one of these two vectors, I can get to anywhere on the plane. And the picture-wise, we end up with this red plane. All right. Ooh, there we go. All right, and as you can see, like, so these two vectors lie in the plane, and we're going to monkey about with it. And we could draw a similar picture for P2. Right, now what did the question want us to do? It wants us to find the Cartesian equation of L, some angles going on. I'll bring these back up as we go through it, and then we're going to show that the two planes aren't perpendicular, and then we're going to rotate one of them. So lots to crack on with. Let's do it one at a time. All right, first part of the question, find the Cartesian equation of L. Now, to do that, we're going to look at the equations of the two planes in a slightly different way. We are going to go to the Cartesian equation of a plane. And to do that, if we look at these two vectors that we have, we are going to add one in, hopefully this one. There we go. And what we're going to do is we're going to take this vector here that is perpendicular to those two vectors. And if I can get a vector that's perpendicular to those two vectors, it is perpendicular to the plane. There we go, a side-on view. There we go, perfect side-on view. All right, so the two vectors lie in my plane, and if I get that blue vector that's perpendicular to the two grey ones, then it will be perpendicular to the plane in general. All right, and I think I've added one in here. There we go. I'm going to get rid of some of these to make our point a little clearer. There we go, right, and same vector is just going through the origin instead of going through the point, right? These two vectors are parallel, and I can put the vector anywhere, but it will be perpendicular. So that's our job. We're going to do that. Okay. Interruptions. Let's get a pen going. Let's start out with a nice black pen. Color. Okay. Right. So, part A, part I. Now, to find a vector that's perpendicular to two other ones, the best way for us to do it is to do a cross product. Ooh. There we go. Naughty pen. All right. So we get 6 minus 0. I'm not going to go into detail about finding the cross product. You can look that one up. This will be a 0. It's a very simple calculation. And then minus 2, 6, 0, 2. Now, in general, then, the equation of a plane, if we say r is the position vector of a point, I'll pop this up here for you to remind you. All right. So a plane can have this form of an equation. R dot n is equal to some constant, where n is a normal vector to the plane. Again, not going to go into huge detail on that form of the equation of a plane. Go look it up. So this tells me that pi 1 can be written in the form 6x plus 2z is equal to d. Now, how am I going to find d? I need a point on the plane, and I've got one. I've got the point 1, 2, 3. So if we plug that in, x is 1, z is 3, I would get 12. So I get 6x plus 2z is equal to 12. Excellent. And we'll do the same thing for pi 2. 1 minus 1, 2, crossed with 1, 1, 1, is gonna give me minus 2. Is that right? Minus 3 even. Minus 3. Come on, we're better than that. We are better than that. We're the further maths crew. Minus 3. And then 2 minus 1, I make that a 1. And I make that a 2. So pi 2 is going to have equation minus 3x plus y plus 2z. And again, we need to plug a point in. We'll plug in the point 0, 1, 2. So I think that gives me equals 5. All right. Now we're still not there, but we do need the Cartesian equation of a point in there. And again, let's go back to our Cartesian equation of a line that lies in both planes. So having done that exercise, I'm actually able to draw both planes. I've now got the blue plane and the red plane. Now, the line that we are looking for that lies in both of them is going to be here. It's going to be here. It's this line of intersection. That is where I've got a line in both of them. All right. So in fact, it will be, bosh, that green line there that hopefully you can see. All right, that one up there. Now, how am I going to find that? Well, really what I want, what I really, really want, and I'll tell you what I want, is if we have a look like this, let's look at this dead on. What we want is we want a vector that is perpendicular to these two vectors here, like so. And in fact, if I take the planes out, we might be able to see a little bit better. And in fact, what you might be able to see is that my line is going in the same direction as that perpendicular. All right. Now we can also think of it as such. Right. Let's view it. This vector is perpendicular to the plane. So it's perpendicular to any line in the plane. This purple vector is perpendicular to the blue plane. So it's perpendicular to any line in the blue plane. So because the green vector is in the blue plane and the red plane, it is perpendicular to both purple vectors. So it's going in the same direction. So again, we're back to another cross product. I need to find a vector that is perpendicular to both of these normal vectors. All right, so that's my job. And then I'll need a point, and then we can go from there. All right. So what do I need now? We need a pen. There we go. So what we're going to do is we're going to take our two normal vectors. Oh. And we are going to stay on this page. And we are going to take the cross product with minus 3, 1, 2. And that will give me a vector which is -2, -18, and 6. Now, we just need the direction of that vector, so we could always rescale it down. So the line L is going to be a point on the line is, we need to start somewhere, and we'll do that in a second, plus some constant times this direction vector. And in fact, I'm just going to scale it down, divide everything by -2. That looks like a 0 and a 1, best case scenario. See if you can spot the guy that's still getting used to some of his IT equipment here. All right. So now I need a point that's on both planes. Now, the way to do this, you can just pick one of the coordinates at random. I like to start with x is 0. Why? Because I can. And then we can get from this first one up here, from the equation of pi 1, then that z has to be equal to 6. And then to find y, I'm just going to plug both of them into there. So I get 0 plus y plus 12 is 5. So I do get y is -7. So the equation of the line is going to be, the equation of the line is 0, -7, 6, plus some scalar times our direction vector, which was 1, 9, -3. Right, let's finish this part up here. We want this as a Cartesian equation, and we'll take the time to remind you of this one. If I spell this out in terms of the three components, I get x, y, z is equal to 0 plus k, -7 plus 9k, and what was the last one? 6 minus 3k. And then all I need to do is rearrange each of these for k. So x is equal to k, k is y, plus 7 over 9, and then z -6 over -3. The standard way of going from the vector equation of a line to the Cartesian equation of a line. So like I said, this question is going to take us on a wild tour through all of 3D geometry. It's absolutely amazing. Right, part 2. Let's find the values of the causes between the axes, basically, and the line. Now, what we're going to use here is, I'm going to remind you of this, and we're going to use this a lot today, that the dot product between two vectors can also be given as the modulus of A, modulus of B, cos of the theta between the two angles. All right. So really what we're going to try and do, and we're going to hop back over to Desmos as I look over to this screen, and then back up to this screen. Right, let's get rid of some of the extraneous fluff, and we're going to get rid of V1 and V2. Now, when we're talking about the angle that this line makes, really, we just need the direction of it. So that's why I've still got my little vector here down at the origin, and that will let me compare it to the 3 coordinate axes. All right, so I've put these in green. Bosh, bosh. All right, so what I'm going to want to do is to find the, and I can do all kinds of views on this. Bomb. Let's get rid of the line as well. Where am I? Let's get rid of the line. Okay. So where we want to be is the angle between the line and the x-axis is essentially that angle. Between the line and the y-axis is this angle, and the z-axis is this angle. And to do that, we are very much just going to use, that's better. We are very much just going to use, there we go, the dot product, like I just pointed out to you. So, where are we? Where's my cursor? There it is. So first things first, we want with theta x with the x-axis, so we're going to take our direction vector, 1, 9, minus 3, dotted with the vector 1, 0, 0, is equal to the length of that bad boy, which is square root of 1, square root of 9, 1 squared plus 9 squared is 82, square root of 91. The length of 1, 0, 0 is 1, and that will be cos theta x. That tells me that cos theta x is equal to 1 over square root of 91. And we can tidy that up if we want to, but I don't know. Let's not take the risk. It's 91 over square root of 91. And we can do the same thing. We can do the same thing for 1, 0, 0. 0, 1, 0 would give me 9 equals square root 91 cos theta y, which tells me that cos theta y is 9 square root 91 over 91. Once we've, look at this, look at this, look at that mess over there. Carried away. There we go. Once we rationalize it, I wonder how many of you already typed comments. Keep me honest, keep on track of these things. Mistakes do happen when we're streaming these things. In the same way, I'm just going to jump straight to the answer then for this one. You probably got the right idea of what's going on. Root 91 over 91. And bosh, bosh, bosh. Excellent. All right. So part 1 done. Part 1 done. Where am I? Aha. Okay. Prove that pi 1 and pi 2 are not perpendicular. Well, to do that, there it is. We just need to look at their normal vectors. And again, I suppose, like I said, this is more of it's a teaching opportunity as much as anything else. So we're going to get rid of that. We're going to get rid of these 3. We don't want them. See if you can spot where in my eye line my Desmos screen is. Now, the idea is this. If I want the angle between the two planes, there we go, is either that angle or that angle, depending on how you want to define it. That's absolutely fine. Quite often we take the acute one, but just bear that in mind. Well, in fact, a very easy bit of geometry, because these two things are normal, you should be able to see that that angle there is the same as that angle. So the angle between the planes, we can just take the angle between the two normals. And that's what we're going to do. And that is what we're going to do. Right. So just a reminder, pi 1 was 6x plus 2z is equal to 12. Pi 2 was, where's my crib sheet? Minus 3x plus y plus 2z is 5. And the only thing I really want here are the two normal vectors. So what we're going to do is we're going to use that same identity as before, 6, 0, 2, dotted with minus 3, 1, 2, is equal to the length of this bad boy. Length of a vector is just Pythagoras. Length of this vector, which I think is 14, minus 3 squared, 9, 1 squared, 1, so 10 plus 2 squared. That does look about right. Cos theta. Now, if all I care about here, I don't actually want the angle between the two. I just need to show, well, I will actually, but prove that they are not perpendicular. Now, if they were perpendicular, this is part B, and at the moment we're doing part I, cos theta, so theta would be 90 or pi over 2 if we're using grown-up measures, and then therefore cos theta would be 0. So basically, for them to be perpendicular, their dot product has to be 0. And of course, we can very easily see here that minus 18 plus 0 plus 4 is not 0. Therefore, pi 1, pi 2 are not perpendicular. So find the acute angle between them. Well, we're just going to finish this. So minus 18 plus 4 is minus 14 is root 40. I suppose we could simplify that. Root 40 is 2 square root of 10 times square root of 14 cos theta. Now we want the acute angle, so we're going to deal with this in a second. But that gives me minus square root of 14 over 2 square root of 10 is equal to theta. Now what do we want? Find the acute angle to 3 sig fig between the two planes. I'm going to assume that we are in radians because we're doing further maths. How have I marked that up? 14 over root 14 is root 14. We should be fine. Am I in radians? I am in radians. So let's just ask it the big question. Yo, calculator. Using the big boy. Minus root 14 over 2 square root of 10. Minus root 14 to root 10. And I get theta is 2.204. That's rounded, but I'm going to do something a bit more with that in a second. But that is the obtuse angle. All right. Let's go back here, just double check that we are okay with that. Sorry, I keep creeping off screen. All right, so what we've found is we found that angle there, which is this angle here. So to find this angle, it's just a case of doing pi minus. All right, so we're going to do pi minus the answer. So this is, we could always, oh, where'd you go? Say that that is obtuse. And therefore, after dropping all our stuff, like some pro, we're going to go that my actual acute theta is pi minus that, which is 0.9. Oh dear. So what happens when you're not looking where you're writing, everyone? Oh, look at this. Oh, some absolute pro moves going on here. 0.938. Okay. Okay. So far, so fairly standard. Now here's where we're getting into the meat and potatoes, the good stuff. Determine the shortest distance from the origin to pi 1. Now we're only going to be working with pi 1, which makes the geometry of this a lot easier for me. And here we're going to go back to Desmos for a little bit, if I can get the mouse cursor. All right, so we don't care about pi 2 anymore, so we don't care about that. I'm going to leave this vector on for a bit. I want to whack back in the points that we had on the plane here, my point A from way back at the beginning, if you remember that. Now, let's go side on. Now, the nice thing about pi 1, which I think is why they're asking us to do this, is it doesn't have a y part of its equation. And if you have a look here, you should be able to see that it is constantly, like for any given value of x, for example, the y is constant. So it means that I can actually look at this side on quite nicely. So the distance we want is from there to there. Right. That's not a point I want. What I want is this. Bosh. Something else. All right. Now, all I've drawn here is I've drawn the line from my point on the plane, the one they gave me originally, and the origin. Now, the distance we want is right here. But this has formed a right angle triangle. This normal vector there, yes, it's a bit too big. And to be fair, I've resized that one. That is too big as it is. I just resized it to view it nicely. But that's the direction we want, and that's all we care about. So we're going to have to try, I'm going to try and draw a quick sketch of this over on our question. But that's our plan. So this is what's happening. When you see my next sketch, this is what we've done. We're just looking with the y-axis straight on. Right. So let's go over to here somewhere. Not there. That is nowhere near where I wanted it to be. All right. All right. So if you remember from our little sketch there, let's get ourselves a different color. We've got our plane coming in like that. And we've got point on it. Oof, that is bad. That was bad. That was equally bad. All right, let's try this again. Do not have all the pro moves yet. Actually, let's go get a different color. Yes, that's what was wrong. It was the color, obviously. All right, so we know this thing here. All right, that's my normal vector. That's my point. All right, that's my point. Now, ideally, what we want is if I have that vector, the distance I want is from there to there. Now, I can find that length. I can find that length, call that length there L. All right. And in fact, if I call this point here A, if I call that point there A, that is, if PowerPoint can stop being super helpful, is the length OA. And what we can see is that D is the length of OA times cos theta. All right. And that's what we're going to use. Now, depending on your exam board, you might get given the formula for the distance between the shortest distance between a point and a plane. I don't know. Some exam boards do, some don't, which is why I think it's always useful going back and looking at the geometry of this. Now, the next thing we're going to use is, we do know this normal vector here, n. So we can use the fact that OA dot, if that's a vector dotted with n, is equal to the length of OA, length of n, cos theta, which does mean that the length of OA, so OA dotted with n over the length of n is equal to the length of OA cos theta, which is that distance we are looking for. All right, so first things first, probably we need to find the length, what the vector OA is. A was the point, if I remember correctly, and I'm just going to look it up, was the point 1, 2, 3, the one that they gave us early on. So what we're actually doing is the vector 1, 2, 3 dotted with that normal vector for the pi 1, which was 6, 0, 2, over the length of that normal vector, square root 40, and that will equal to the distance that I want. Let's double check my numbers. Oh, recording in the home studio, love it. So that gives me 12 over square root of 40 is D. So what does that give me? 12 square root 40 over 40 is D. Root 40 is 2, so I can divide the top and bottom already by 4. Divide top and bottom by 8 to get 3. Not root 40. Idiot. 3 root 10 over 5 should be my distance. Now, let's see. This will make sense to me. So if I go back to this one, you can't see what I'm typing, but if I rescale this, I should be able to times 3 square root 10 over 5. Ooh, that did not work. So why is that? Oh, square root 40. There you go. And yeah, so that looks like the correct answer. What I've done is I've made this the right length just by using those numbers we got. I wouldn't worry about that too much. But yeah, so there we go. That is the geometry that we end up doing for the distance between a point and a plane. And whatever that formula is that you get given, that is what's going on. And you can actually extend that to 2D as well. if you're being extra funky about it. All right? Okay. Staying with me, you're doing really well. Like I said, this is a huge chunk of 3D geometry going on. Now, this one here, the plane is rotated 90 degrees about the y-axis to give a new plane. Determine the equation of pi1 and state the shortest distance from the origin to it. Now, this is a really nice occasion to actually remind ourselves that state tells me that there should be nothing more to calculate. It should be obvious. No calculations needed for state questions. Bear that in mind. How about we have a little think about what's going on? Again, I'm going to look off screen. You're going to wonder what I'm staring at, but I'm going to stare at this plane. Let's get rid of some of this, and let's get rid of this point. So what are we going to do? We're going to take our plane, and we're going to rotate it about the y-axis, which is here. Generally, when we rotate about an axis, you look at the axis straight on, and then you rotate, and same as always, clockwise is negative, anti-clockwise is positive. Depending on how you view it, actually. Because I'm actually viewing it straight on, we're going to go the other way around. So honestly, yeah, so we are actually going to take clockwise around the y-axis because we're looking at the y-axis straight on. Not always the easiest to remember that one. There are some allowances made, but yeah. So if I have the y-axis here, I mean, fundamentally, as he rabbits on, trying to justify his existence, remember, like, in the xy plane, if we view the xy plane like this, to view the xy plane like this, z is coming directly out at us, out of the plane. Which I think this has quite a nice, there we go. Now, in this case, a positive rotation is anti-clockwise. So positive rotation is anti-clockwise with with the z-axis pointing straight out at us. So if I want to rotate around the y-axis, let's put the y-axis pointing out at us, and then let's get our plane back in. So really what we want to be doing is we want to be rotating it 90 degrees anti-clockwise. Now to do that, we could just rotate its vector. They're different sizes now because I've resized that one. Let's unresize that one. Only really the direction matters to me. Oh, wow, I haven't even... there we go. So one thing we could do is we could just geometrically, just pure geometry, rotate it round. All right. So I'm going to take my normal vector and rotate it 90 degrees. Now, very simple geometry will do that for me. Very simple geometry will do that for me. So if you think of this, if you remember what my normal vector was, okay, it's going along 6 in the x direction and up 2 in the z direction. So as you can see, what we want it to do, we want it to go 2 in the x direction, but -6 in the z direction. And then we just need a point. Now, let's take here. This is x is, I think it's x is 2. Yeah, it goes through x is 2. Now, as I rotate this, we're going to go to z is 2. X is 0, y is 0. So then we get our point. I hope you followed that. Let's go back and try desperately to draw this. So my new normal vector, we said, was instead of going along 6 in the x direction, it's going down 6 in the z direction. Still nothing in the y direction, and there we go. And you can check that if you dot that with take the dot product of this with the normal to the other plane, you will get 0. And then the point on the plane, we said instead of going through x is 2, y is 0, z is 0, it's going to be going through x is 0, y is 0, z is -2. So the equation of my new plane should be putting all of that together. Well, actually, this is a point, isn't it? 0, 0, minus 2. 0, 0, minus 2. So we get 2x minus 6z is equal to a constant. We can plug this in, and that constant is going to come out as 12. Excellent. Minus 6 times minus 2 is 12. Brilliant. So that is one way to do it. Now, again, depending on the exam board, you might have done some rotations in 3D. So I am going to go through doing that as well. So this is option 1, just doing it with pure geometry. Now, obviously, I'm at home, I'm mucking about with, or trying to, with a whole bunch of stuff. Oh, look at that, another pro play. And I'm able to go on Desmos and watch a lot of this. Obviously, in an exam, we don't have that option. So the other thing is you could just take the vector of a rotation. Now, rotating around the y-axis, we can set up a matrix for that. All right. Again, I know AQA, for example, has this in their formula book. It's a bit lazy, but there it is. I'm not sure about some of the other ones. If you're still with me, tuning in, but there's some ton of good stuff in here. Right. Now, let's go get these back. Let's clear the page a little bit. Let's clear the page. Right. Let's get our original view back. Whoop. All right. Now again, we are going to rotate 90 degrees around the y-axis. So let's get our y-axis pointing out at us. And if you remember, for any rotation, we just need to keep track of where everything goes. So the y-axis isn't going to change. And we're going 90 degrees clockwise. So x is going to become, so the I direction is going to become the minus k direction, and the k direction is going to become the x direction. We see that as we move these arrows about. So z, instead of being 0, 0, 1, is going to become 1, 0, 0. Pay attention which way things are going. And x, the I direction being 1, 0, 0, is going to go to 0, 0, minus 1. So that gives me a transformation vector of, so the I direction goes to 0, 0, minus 1. The j direction doesn't change, and the z direction goes to here. So now I can just rotate my line. I can just rotate my line to go 0, 0, minus 1, 0, 1, 0, 1, 0, 0. And we need to rotate a point on the line, on the plane even. Now remember, pi 1 was, and actually we're going to go back to the vector equation of this. It was the point 1, 2, 3, was it not? Was the point 1, 2, 3? Plus lambda lots of, I could just go back to the original question because I don't have it written in front of me anymore. Plus lambda lots of minus 1, 2, 3. Plus mu lots of minus 1, 0, 3. Going to be quite useful to me in a second. Oh, trying to keep on track of my, this is stuff what I did earlier. So if we times this out, I get 1 minus lambda minus mu. I get 2 plus 2 lambda, and I get 3 plus 3 lambda plus 3 mu. If I do that, what do I end up with? I end up with Bosch, I end up with 3 plus 3 lambda plus 3 mu. Second line, I'm just going to get the 2 plus 2 lambda. And the third line, I'm going to get minus 1 plus lambda plus mu. There might be better ways to do this. Please do tell me. So this tells me that my new rotated plane, pi1 dashed, is r equals 3, 2, minus 1 plus lambda lots of 3, 2, 1 plus mu lots of 3, 0, 1. And we can get that back into the Cartesian equation of a plane, just like we did before. So we'll go 3, 2, 1, crossed with 3, 0, 1 to give us 2. That's a good start. 0, that's a very good start. 3, 0 minus 6 is minus 6. That's a very, very good start. So we will get, why am I scrubbing that out? There we go. 2x minus 6z is some constant. Did I get this point correct on the plane? I've said it goes through the point 0, 0, minus 2. But we could just put in the 3, 2, minus 1 as well. 2 times 3 is 6, minus 6 is 12. So no matter what, we get the same answer, whether we do it like with that more intuitive geometry or like pure brute force or rotational stuff. And there we go, an absolutely whopping, how many marks with that? 8, 10, 15, 20, 23 marks. Now we took our time on it to go through and review a bunch of little things with 3D geometry. Hopefully some of those pictures helped you out, visualize all the things. And I didn't just want to use the formulas and crank through this, because I could have done, we just go through it, but actually it's a nice little way to review heading towards that exam season, all these different things that you can do in it. I love a bit of 3D geometry. I love some of the ways we twist around it. I might try and find a couple of questions that involve the cross product as well. But there you go. Hopefully you found that helpful. I'm going to go pass out in a corner after that. I'm Nick. This was some further maths. If you enjoy this format of a video, maybe not this long, do let me know if you find it useful. Drop a comment, a like, a subscribe. Let me know so I can produce the content that you find useful. All right then, I'll see you next time.